My name is G. Nikhil Reddy from IIIT City. Today I'll be presenting on my HTL project. And my HTL project problem statement is FPGA CNN Hardware Accelerator for classification of UAVs with living objects. So why this? Why this problem statement? So in the recent years, the advancement in the UAV, that is the unarmed vehicle, aka the drone technology, has been increasing by a lot of factors, and the drones are getting smaller, faster, more agile, more efficient, etc., and with more payload capacity. Let's say this technology were to fall into our enemies' hands, and they were to deploy the drones uh, in our country, and since these drones are unarmed and they can control themselves, they can execute their target mission and maybe damage our country or maybe carry out assassination attempts. So this kind of technology, if fallen into a wrong hands, they can pose a great threat to our nation's sovereignty. So today I'll be implementing a neural network model where it will classify drones from birds and other things such as humans or corner reflectors. So this can be done in cloud where we can feed the data into the cloud and we can use the AI agents over there. But these kind of missions require low latency, and they require precision. So I think using FPGA board and building a neural network net will save us a lot of time and a lot of resources also, and we can also stop the enemy. So let's say how I implemented it. So I implemented this paper, uh, which is by Emre Can Ertiken and Selda Gini. So the paper is classification of targets by using frequency modulated continuous wave radar data with machine learning techniques. So basically what they've done, they've taken a data set uh, which was captured by a radar, and they've classified the data set into drones, birds, and humans and corner reflectors, and their subgroups also. So what they've done is they've taken a six-layer CNN, 2D CNN model, and they've generated spectrograms from their radar data. So these are the spectrograms which they have generated, and these have a resolution of 100 by 100 pixel. So they pass the spectrogram to the model, to the CNN model, and with this they can classify whether the whether the given data set is a drone, is a bird, or is it something else? So the data set which they've gotten is from Zenodo by KTH Royal Institute of Technology. So they've used a 76 gigahertz FMCW radar sensor uh, to acquire the data. So as you can see, there are 130 rows and six columns. This is a 130 by 6 cell matrix, and column one has the data classification drone, D1, D2, D3, D4, D5, D6. These are different type of drones. Human walk, human run is a different type of human actions. Seagull, pigeon, raven, black-headed gull, seagull, heron are a different type of birds. Seer is a triangular corner reflector. So they've used these test subjects and obtain the data. So column 2 is a complex value data matrix of scan segments with 1280 rows in one column for each scan segment. Column 3 is range in meters to center range cell. Column 4 is time in seconds. Column 5 is indicator whether the sample that we are using right now is a training set or a validation set or test data set. Column 6 is a binary indicator with logical 1 if the target is close to the field of view edge. So let's go to the local machine where I have executed the code. Uh, so, so this is my code. I'll use numpys here. I've loaded the dataset and using the dataset part. So this is my dataset, dataset.numpy. This is a 1.45 GB. Loaded the data set. Explored in this first .apynb file. I've explored through the whole data set. So this the shape is 130, 6, and these are the labels: IQ data, range, time, split flag, and H flag. And this is the and I've explored the data set. So there are a total of 75,868 scan segments. So that's around 76,000. And out of this 76,000 scan segments, the D5 subclassification of drone dog has the most scan segments with the 12,000, followed by D6. And at the last, we have the label. So from this, we'll extract 64 features. So, the thing with the original paper is that we can't implement that in my PYNQ Z2. So I'm using a PYNQ Z2 board, and it has a DSP slices of 220. The number of DSP slices that are present in the PYNQ Z2 is 220. And let's say if I were to uh, physically implement the paper, then I would require around 1,000 DSPs, which is obviously impossible. So what I've done, I've scaled down the model from 2D CNN to tiny 1D CNN with 3 convolution layers and 1 FC layer. So for the tiny 1D CNN, I've extracted 64 features from the 1280 element complex IK vector. So from that, 0 to 32 cells have power spectrum of center range cell. 30 to 48 have magnitude variance. 48 to 63 have their per range cell statistics, that is mean standard deviation dynamic range. And the 63rd cell has the mean phase difference. So using this data, we'll calculate the will train the model and then classify the data. So I'm reshaping. So this is I'm explaining the data by reshaping and by downsampling them. So this is the whole code. So feature vector has a shape of 64 comma. Feature range is 0 comma 255, and these are the first 10 features. This is the class mapping. So as I've said, there are several classes, and there are 4 classes, and those four classes have several subclasses. So what I've done, instead of operating with the subclasses, I'm operating with the superclasses. So D1, D2, D3, D4, D5, they fall into the drone category. So etc. etc. So I've done this, and we got 4 superclasses: drone, bird, human, and corner reflector. And here, I'm building the feature data set. So I'm segregating the data according to the training data, validation data, test data. So this is the process. And I've processed around 75,068 segments. And I've converted them into NumPy arrays. So class distribution, this is the class distribution. And I've saved the train data, validation data, and test data. So let's move on to the next code, which is the training. So as you can see, I'm using NumPy and uh, PyTorch to train the data. Uh, so I'm initializing my tiny CNN 1D model here, and these are my resource budgets. So it's the estimated max and the DSPs that will be used in FPGA. They're theoretical. Uh, and now this is the tiny 1D CNN. So this is the function written for tiny 1D CNN, and now I'll be initializing it. So this is the model architecture that I opened. So convolution layer 1, convolution layer 2, convolution layer 3, and FC. So the remaining are batch norm and pools, which are not required as of now. So what we need to know is that there are 3 convolution layers and 1 FC layer. So I'm loading the data, that is the training data, validation data, and test data. And then I'm converting them to tensors. This is my tensor library. Now I'm training the data. So I'm training the model using the data. So I've used Adam Optimizer and trained the model in 40 epochs. So as you can see, this is the progress. In 40 epochs, my best validation accuracy that I obtained is 93.56%. And this is the progress. So with each epoch, the loss is decreasing, and with each epoch, the accuracy percentage is increasing. Now we'll evaluate the test set. So we'll be evaluating the test set by using the test data set. And validation set, and this is the test accuracy we have obtained. So this is the 93.54 percentage test accuracy overall, and this is the per class accuracy, and this is the confusion matrix we've obtained. So by looking at the confusion matrix, we can observe that the model is more confused between drone versus bird classification, and this is the most important area because there are only two aerial objects in our whole data in our classes. That is one is drone and another one is bird. So the drone versus bird has the utmost importance, and with I think enough resources, I think we can classify them also with lower miss percentages. So now, since I've trained the model, I'll proceed to export my weights to my HLS. But the thing with my Think board is that it is resource constrained, and my local machine, that is my PC, is not resource constrained, so it operates on the floating point 32. So I'll convert into int 8. I'll quantize it into int 8 so that my pink board can operate this flawlessly, operate this model flawlessly. So I'm reloading the model. This is the code, and then I'll use code to fuse the batch norm into convolution weights, and I'll quantize the everything into int 8. As you can see, I've quantized everything into int 8 instead of float 32, and I'll verify the quantization. This is the code to verify this. And then after this, I'll export the C header for HLS. So this is one C header for HLS. So weights.8h, I'll export that, and I've exported that. And also, I'll also save the NumPy weights. So this is over. Now I'll go to generate real test bench. So this code will actually generate test bench for my HLS code, that is the TB code for simulation, to verify whether my given .cpp main code works or not. So this is my tiny CNN 1D function. I'm initializing this, and this is the entire code to do this. And so you can see we've gone through every layer, and now I'm verifying. And now I've exported the weights. So this is the whole weights.h has been exported. So weights.h contains the weights and biases of the neural networks, by which we can reuse them in our HLS module. And I'll also be exporting the test bench because I need it to verify my model. So this is the whole scenario for my divider. For the ping, I'll be choosing 40 raw IQ samples from my data set, and passing and saving a file so that I can use the .npz file in my ping and process it. And I've also saved some weights into the ping. Now let's go to my HLS and see whether my 4 works on me. So this is my HLS. White is HLS. GUI. So this is my main function, CNN Axel.cpp, and the other two are header files. And in test bench, there's a testbench.cpp. So basically, that's the test bench that we've been talking about. So if you look into the CNN Axel.cpp, we've imported the header files, and also we've initialized written a function. So here I will load the data set, I will load the weights, and then I will pass it through every convolution layer. So after every convolution layer, I will re-quantizing as to not acquire losses. So this is quantizing in stage 1. After convolution layer 2, I'll re-quantize it again. And after convolution layer 3, I'll re-quantize it yet again. After that, I'll pass it to the fully connected class, and from there, I'll pass it to the argmax. From there, I'll get the prediction from the model. So let's put it to the test. So this is my test bench. I'll briefly explain this. So I have 20 data sets, 64 feature sets, and this is for loading the data set, loading the weights. This is for initializing the function, and this is for seeing whether the output that we've gotten from the model is correct or not and matches the model working on it. So I'll run this dataset, which usually takes 5 seconds. So let me run this. It's running, as you can see, and you should get our outputs by any link. So we got in our outputs. So as you can see, uh, out of the 20 test cases, 14 are correct. That means we have attained an accuracy of 70%, which is good for a 1D CNN model, which is operating on n intake. And this match specifies whether our model is working in accordance with the uh, real model. So as you can see, we got a match of 20 by 20. So out of 28 test samples, our model has worked exactly like you predicted. So, and that's why this model is a flawless model and our test cases passed. Now we'll run the synthesis. After that, we'll run the implementation. And then after that, we'll export the RTL code so that we can RTL code as the IP. So we can use that IP in our Vivado and construct the block diagrams. So I've already ran synthesis and the implementation since as they take too much of time, as a consume time. So this is a synthesis summary. And there's a bit of slack, but that's negligible. This is a synthesis summary, overall synthesis. And if we go to the implementation and we look at the resource usage, uh, there are 23,627 LUTs have been used, and flip-flops are around 8.5K, and DSPs we've used around 212. So which means we've used around 96% or 96% of available DSPs. So we have around 220 DSPs in Uplink, and we used around 212. And DRAMs are 36 DRAMs are used. So this is our implementation report. After that, I'll export the RTL. From the RTL, I'll get the IP. Exported RTL, I'll get the IP, and I'll use that IP to build my block diagram. And from there, I'll generate my big string in Vivado. Let's go to Vivado to analyze our files. Analyze our IP. So this is our IP. So this is our Vivado. I'll expand this. So this is my IP, exported IP, the custom hardware that I've made. I'll zoom into this. So this is my custom IP that I created as block, reset, interrupt, and a SAXI control. And this is my Zinc processing system, basically the PS part of the PYNQ board. This is the process system reset, and this is the AXI interconnect. And this is GPIO. The GPIO is used for controlling the LEDs. When the classification happens, the LEDs blink in order to tell us what has been classified. So this is the overall block diagram. This is the overall block diagram of my board of my model. Now what I'll do, I'll run synthesis, I'll run implementation. So they consume time, the synthesis and implementation, they consume too much of time. So I've implemented them beforehand. So this is my synthesis and this is my implementation. As you can see, DSPs are 212. The number of DSPs that I use are 212, flip-flops and LUTs. So this is perfect. So this board is, we can generate the bit stream because the synthesis and implementation is now successful. But before generating the bit stream, we should also generate its hardware handoff file. The hardware handoff file is used when my pin code about the hardware that we're using, that is the pin code. So I'll click on generate and I'll generate my hardware handoff file. And from there, I will go to my bit stream. So I'll generate bit stream. As you can see, I've already generated the bit stream, so it's not required to run it. So I'll use the generated bitstream and the generated hardware handoff file and export it to my PYNQ Jupyter notebook. So this is my This is my Jupyter homepage, in the Jupyter Notebook homepage, and this is my overall .ipynt file that I'm going to execute. So this cell loads the bitstream CNN overlay bitstream and also loads the CNN overlay hardware handoff file, and it will also get the required functions ready. That is, it will extract the features and also classify the FPGA. Now I'll do the live classification. This is the HTML code that I'm going to do, that I'm going to present here in the form of GUI. So this will update dynamically in real time with the classification results. And from there, I'll generate all the results. I'll generate spectrograms. I'll generate confusion matrix, radar signal analysis, and everything that is required for us to operate the FPGA, analyze the FPGA. So I'll go on to the uh, implementation part. After this, let's go to our outputs and then check whether our implementation has been successful or not. Is successful or not? Let's go to my file system. Let's go to my file system. So here I'll go to my outputs. So these are the entire outputs I've generated. So as you can see, this is the per class accuracy of the test data set that I've given to my PYNQ, and this is what I got. So this is real time. I've done this in my PYNQ board using the real hardware that was given in the PYNQ board, and I've got these results. So for every word data set, the class accuracy is 100% because the board is, for some reason, it's identifying the birds very accurately. It has an accuracy of 100%. Drones have 90%, humans have 70, and the CR has an accuracy of 100%. We'll go to the confusion metrics and we'll see that we've got this. This is a predictor and this is a true neural. Now we'll go to our Doppler spectra by class. So this is a Doppler spectra by class. And these are the feature vectors that are used for a model by a model. So these are the feature vectors for drone, bird, human, and the CR. So these are used to train a model and then classify the test data set. And this is the phase variation. The 63rd cell that we've been talking about, that we talked about, states this phase variation. This is the range profiles by class. This is the FPGA resource utilization, 212 DSPs, 212 by 220, LUTs and DRAM. This is the radar return strength by target. This is the drone, bird, human, and CR. And this is the micro Doppler signatures. So we can use this micro Doppler signatures in the 2D CNN. But since I'm resource constrained, I can't use this. But in higher boards like Kriya or some other boards, we can actually use this micro Doppler signatures and get a another model with higher accuracy. And this is the FPGA inference latency distribution. So we took our mean time is around 1251 microseconds, and this is the main part. Our ARM CPU took around 2,54,501 microseconds, while the FPGA took around 1,810 microseconds. So as you can see, this difference is huge and is very important for time critical missions. Let's say a drone were to assassinate a high-ranking government official. So we need this speed up to disrupt the drone's path and then save our country. And this is our FPGA inference latency. This is my whole project, and that's it from my side. And hope this project serves some purpose in the future. Thank you.